This must be one of the most common misunderstandings about quantum mechanics, that quantum mechanics is about making things discrete. But it is an understandable misunderstanding because the word quantum suggests that quantum mechanics is about small amounts of something. Indeed, if you ask Google for the meaning of quantum, it offers the definition: a discrete quantity of energy proportional in magnitude to the frequency of the radiation it represents. Problem is, just because energy is proportional to frequency does not mean it is discrete. In fact, in general, it is not. The reason that quantum mechanics has become associated with discretization is entirely historical. The first signs that something was not quite right with the fundamental theories of the 19th century came from atomic spectral lines. Atoms can absorb and emit light only at certain frequencies. If you think that atoms are basically blobs of particles stuck together, which was what people thought at the time, then this makes absolutely no sense. According to quantum mechanics now, the negatively charged electrons occupy shells around the positively charged nucleus. These shells cannot have any radius, but only certain values of the radius are allowed. Just what shape the shells have and how large they are can be calculated with quantum mechanics. And this explains why atoms can only absorb and emit light at certain frequencies, because the energy of the light must fit to the energy that moves an electron from one shell to another. So yes, the energies of electrons which are bound to atoms are discrete. But the energies of electrons, or of any particle really, are not always discrete, and neither are other measurable quantities. The energy of a photon traveling through empty space, for example, can have any value according to quantum mechanics. The energy is not discrete. Or if you look at an electron in the conducting band of a metal, it can be at any position. The position is not discrete. What then does it mean to have a quantum theory as opposed to a non-quantum theory? A quantum theory is one in which you have observable quantities that obey Heisenberg's uncertainty principle. Mathematically, this is not entirely the correct definition. More precisely, a quantum theory has operators for observables which do not commute. But for what the physical consequences are concerned, the uncertainty principle is what tells quantum from non-quantum theories. The other important property of quantum theories is that you can have entanglement. We will talk about what this means another time. For today, the lesson to take away is that quantizing a theory does not mean you make it discrete. This is important also when it comes to the quantization of gravity. Quantizing gravity does not necessarily mean that space and time have to be discrete. Thanks for watching. See you next week.